Okay, it's time for us to do the LeetCode daily questions. So today is May 14, and we are going to do a medium question. So today's question is 114, flatten binary tree to linked list. And yeah, it's probably a classic question because it's under 400, and then there are 4,000 upvote, only 400 downvote, but I think 400 is also a lot. But for 4,000 upvote, so I think probably this is a question for a basic practice of something. Um, yeah, so let's try to see if we can solve this before the deadline today and submit it because I can't afford to use another. Well, I actually don't qualify to use another time travel ticket again, so I need to solve this before the deadline. So let's try to see if we can solve it together. So first, let's read the question together. So it's flatten binary tree to linked list. Given a root of a binary tree, flatten the tree into a linked list. Okay, so the linked list should use the stem tree node class where the right child pointer to the next node in the list and the left child pointer is always null. So there is a, oh, okay, so there is a data structure they define, a class that they define a tree node. So they want you to directly use the tree node to form a linked list. And then the way that you use it is to keep the left pointer always null and then use the right pointer as the linked list pointer to the next node. Okay, so the linked list should be in the same order as a pre-order traversal of the binary tree. Hey, okay. So I think this is probably a practice of doing like a pre-order traversal, right? I think so. For the pre-order traversal for this binary tree is pre-order. So we say we use the current node first, and then we output all the thing in the left and then all the thing in the right. And then for the thing in the left, we also output the current node first, and then we output all the thing in the left, the rest in the right. So it's 1, 2, 3, back, and 4, back, and 5, and there's no left child, and 6 times. So this one, if you do the pre-order traversal, it's based on the number is actually the order of the pre-order traversal. So they show you that you have to use the right child as the node, the linked list pointer to the next node, right? So it will become this. So it will be like that. You do a pre-order traversal and you link this to this 2 to 3, and then you link 3 to 4, and then you link 4 to 5, and then you link, no, you don't need to change the link. Yeah, so actually, well, it could be as easy as just doing a pre-order traversal, right? So this is the example picturing here. And then they tell you that if the input is null, just return the null node. And if the input is the one node, then return one node. Okay. So, and the range, the number of node, so there will be less or equal than 2000 node, and then each value will be between negative 1000 to positive 1000 range. Follow up, can you flatten the tree in place? Okay, let's not do the follow up first. And maybe the hint is related to the follow up, so maybe we don't need to see the hint. I can't help but want to check the hint. But because we already know we are going to do a pre-order traversal, which means we are going to do a depth first search, right? Or recursion. I mean, actually doing a recursion. We put this and recursively call the pre-order traversal on this, and then call the pre-order traversal in this, right? Since we already know the way to solve it, let's check the hint. Why not? If you notice, okay, so yeah, right. So the hint is actually for you to do the flat follow-up, right? So let's not do the follow-up first. Let's try to do the regular one, okay? So, and the regular one will involve recursion. So you won't be use constant extra space. You will use a stack, well, a system stack to be specific. Okay, I can't speak right now. So let's try it. So you have a flatten. Can I recursively call the flatten? And oh, so you're not returning a root. You are just relink those thing, right? So okay. So what will I do? I have a current row. So it's probably still easier for me to do a recursive call on something that will return a return a node, right? Because for me, it's like for this recursive call, I will return the last point of my right child, right? So for example, for the current node 1, I recursively call something in the left child first, right? And the left child will return the last element of the recursive call, which will be 4. Then I can point that 4 to 5. Right? Right. Is that right? I somehow a little bit confused, but then let's do it. So for this, I will just recursive call something called like pre-order, okay? And I will pass in the root. And then let's do private. We will return this tree node, right? TREENODE. And no, return a tree node what? And it's called pre-order. And I will have a tree node, which is, let's call it cur, which means the current node, right? So for this, I'm going to return the last one, because now I'm going to return a linked list, and then I'm going to return my last one, right? So I have my cat in here blocking my screen again, so sorry, I need to move keyboard and say hello to the camera and sleep here, okay. So I need to you sleep here first. Point my right child to my left child, and then point the node, and then point my right child to the node that my recursive call return. Okay, so let's try it. So I am going to so my cur will equals to oh wait I actually don't care about anything that my right child return, right? So how about let's do the, although it's not typically pre-order traversal, so I probably should not name it pre-order traversal, so let's name it DFS, I think. Okay, so because I don't really care about whatever my right child return, so let's recursive call this DFS my cur dot right. Okay, and then I will have a tree node temp to point to my right cur dot right right, and then I will have a tree node, and then my cur dot right will equals to DFS cur dot left. Okay, hold on. So what if my left child is null? So I don't do this. So I'm not going to call this, right? Okay, anyway, so let me do, if my cur dot left is not null, then I do this too. Then I need to keep a copy of my right child, and then I need to do and then my right child will be the DFS of my left child. No. My right child will be my left. Right. And then I can call to flatten my right child, no matter if it's null or not. And then I can also point tree node rest is the one that I want to return, is the one that's in the right child. And so it's already, oh god, what I'm doing. So let me do this first. So no matter right child is null or not, let's do this. But if my left is not null, I move the left to the right, and then I recursively call the left, which will give me the last one of the left, and I will point it to the, okay, so let's do this. Dot right is temp, and then I return dfs temp. Is that right? Okay, so now I don't care about whether it's null or not. But what if it's null? What if my right child is null? Then I have to return the last one, which is when I return recursively call the left, right? Let's do this first. So if so the easiest thing is that I need to make sure that the cur is always not null. So if root is null, then I just return null. Otherwise I call this. So now I know my cur will always not be null. So if cur dot right is null and cur dot left is null. So if they both are null, then return cur. Otherwise, if cur dot left, can spell. If cur dot left is null, then I will just return dfs cur dot right. And then if cur dot right is null, then cur dot left is cur dot right, cur dot right is cur dot left, and we also return dfs cur dot right. So now we get that fixed. We deal with the null condition. So when you reach here, you know that both right and left are not null. So I don't need to care about this. So all I need to do is I need to just make sure that I keep a copy of the right, and then I point my right to my left. Right. So now I flatten this right. Originally it was left. And then this will return a node as the last one of this. And then I point its right to our temp, which is original our right. And then I recursively call this dfs temp so that it will return the last one. Oh. It's a little bit confusing, but I think that's it. I can return null. Okay, so I will just return. So for this, it looks like it's not null. It's just a empty, well, empty tree node, right? So how do we know? Because the constructor, so is that possible that we return a new tree node without having any value? Oh, you can return. You don't return anything in here. So, okay. I somehow forgot. So you only call this when it's not null. Still compile the error. 29. Typo. And cannot find symbol. RIGHT. Cannot find symbol. RIGHT. Null pointer in line 23. Oh, so null could still be null. Okay, so in here I probably somehow what am I doing? So I make sure really it's not null. So I call this. So how would I call this with a null? 1, 2, 3, 4, 5. This is the first test case. So when are we calling it with a null? So if right is null and left is null, then we return the current node. If the left is null, we return. Oh, is that because I forgot a return? Oh. What's happening? 1, 2, 2, 3, 3, 3, 4. Oh god, that's a mess. Okay, so what did I do wrong in here? If less, I flatten the right. If right is null, I move. Oh, I didn't null out the left, right? I think. So cur.left equals to null. And the same thing in here. For every node. So after I move my left to my right, I have to make sure that, let me just copy and paste. I set this. Okay, better. So 1 null, 2 null, 3 null, 4 null. So let's randomly try like 7, 8, null, 9. Okay. Unknown error. Did I do anything wrong? Yeah, but it shows me the tree. So why can I not calling? Okay, it's probably a glitch. 4, 9, 5, 6, 10. 4, 9, 5, 6, 10. So I guess we are good. So the first one, the recursive solution is done. Let me submit. Okay. So the second one is that can you flatten the tree with all one space, which is no space waste at all. And if you notice carefully the flattened tree, each node's right child points to the next node of the pre-order traversal. Okay, So each node's right child point to the, let me, hold on. Let me keep, okay, so let me keep the hint and then picture show together. So if you notice carefully the flattened tree, each node's right child points to the next node of a pre-ordered traversal. I don't quite understand. So each node's right child is pointing to the next node. Each node's right child is pointing to the next node. Next node. I don't actually understand the hint, but from here, because you know that 4, the next one is 5, so you know that there is a link. You are going to link 4 to the 5, right? So I guess that's what they mean. So actually, it's still the same. So in the recursive call, we are trying to make anything that return from the, also it's right, but it's actually left, right? So anything that return from the left, which is the last node of the left tree, point to my right tree, right? That's why for the current node, if the current node is 1, the last node of its left child is 4. And you are going to point 4 to one's right child, right? And the same happens in here, right? So you have 2, 3, 4. So the last one in here is 3. You point to your 4. And in here, you don't have the last one. So last one is yourself. So if you don't have a last one, then you don't need to change anything, right? So for doing it using this method, first, we need to remove the recursive call. So we need to do it iteratively, right? So once we are in here, we probably need to find, or we don't. We can't use a stack. Okay, so what I'm thinking is we still start from 1, right? The thing I don't quite understand is along the way. So if now I move 2 to my right, and then I point 4 to 5, and then I move to 2, and then I move my 3 to... So what if I have more points? What if I have more points like this one? Okay, so when I'm in 1, which is the root, I move 2 to the left. I then try to find the last one, which is 9, and point it to the 9. And then we are done with 1, right? And then we move to 2. And then we point 3 to the... So for 2, because we changed the... Yeah, but... And then to find 9, for the left-hand child, I'm just keep going to the right, right? Until I can't. pre-order traversal. I can't just directly. So for a pre-order traversal, what is the last one? Okay, so for a pre-order traversal, the last one is if your left is not null. If your right is not null, you go to the right. Otherwise, you go to the left. Right? So for this one, if your right is not null, you go to the right. If your right is not null, you go to the right. And you got this one. And what if your right is null? So what if you don't have 4, you don't have 9? Then your last one will be A. So if you don't have right but you have a left, go left and then do the same checking again. Oh, it's a little bit complicated. So let's erase our anyway, I already submitted, so I don't need to keep this. Let's erase it. So today's daily is already done. Now we are just practicing the follow-up. Okay, my cat already finally give me some space to put my keyboard. Okay. So for the following up, we have this. So I definitely need a current node, or I can just use the root, right? So I will do it until there is no left and no right. So still I need to know if the root is null, right? So I still need to this check. If root is null, return. And then while root the left is not null and or root the right is not null. So as long as we are not at the end of because for each point we always link this to that, and then we have this and we link this to that, so we won't reach to the end until we touch the 6, right? That's what I think. Because for each point you always make sure that your left child will not end in the left child, because you always link something in your left child to your right child so that you will continue until the end. So I think this is valid. When this happens, we know that we reach 6. Also, for our example, every time you make sure something in the left will link to your right. And in here, you make sure this will link to the right. So when you go down the tree, you will not, when you reach 7, you already link 7 to 8 when you were in 3. So you won't never end in 7, because 7, when you reach 7 already have a right child, which is 8. So you won't stop in 7, you won't stop in 8, because 8 already linked to 4 when you are in 2. So for this logic, when you eventually reach to a point that they have no left and no right child, it's definitely the last one, and it's definitely the end of the linked list. So I think this works. And now, what we are going to do is we are going to find the last of the left tree and point it to the right tree. We are not going to do this yet. So let's find the last of the left tree first. So you go left. But if you're if okay, so the logic is you keep going to the if you're so let me tree node. It's because we want to last left. Okay, hold on. First, we check if left is null, or while left is not null. Okay, so if left is null, then we just make root equals to root dot right, and then we continue, right? So you continue, because if hello, so if the right is if the left is null, we don't have to do anything, so we just increment like right to the right root to the root right, and then increment, right? Yeah, we already finished. I already submitted this, so I'm just currently doing the follow-up. So yeah, from the past experience, if I don't submit as quick as possible, I will miss that, and I can't miss that. So I will do the tomorrow there is two contests, I think. Yeah, so I will probably doing both. Yeah. So yeah, but now let me finish the follow-up. Although we already submit the today's question, but I'm going to do the follow-up. Oh yeah, but I'm not gonna string for the contest because I think it's not. I don't know. I think LeetCode will consider you cheating if you show your answer. I think so. Right. Yeah. So yeah. So it's okay. Yeah, I can string. Yeah. So yeah, but I will still stream tomorrow's daily, which will include two questions because today is the 7th day of the week. So tomorrow will be the first day, which means that there will be two questions. And then because tomorrow is a weekend, I will think that they will give us a hard question. So, but anyway, let me do this. Let me do this first. So if our left is null, we don't need to do anything, so we just increment to the next step. So we set root to root right, and then we continue. I lost 20 points. Oh yeah, I did it last week. I only finished 2 questions. Yeah. So I stopped looking at my point long time ago. Yeah. So now when we reach this part, we are really sure that we have a left, right? So we go left. Yeah. Yeah. Okay, so we go left and then we check again to see if we have right. If we have right, so if we don't have right, we go to the left. Otherwise, we go to the right. Okay. So again, we will have less left equals to root the left. So I assign the non-null left to the less left, right? So then I will need this condition again because I'm going to find the last one of my left child. So when it is found, it is always the node that don't have a left and don't have the right. Right? I think. So now I assign left to this one and I add a condition of when they are not both null, and if less left dot right is not null, then I increment. Not increment, well, yeah, increment, sort of. So last equals to last dot right, and then we continue. Continue. Why I always can't spell continue? Okay, so when you reach to this point, you do have a right. No, what I'm doing, if your right is null, I am going to do left. Okay, sorry. And continue, right? Otherwise, no, I don't need continue. I only need to do else. We go right. So we only go left when our right is null. I think by this logic we can reach the 4, right? So I get this. I only go left when my right is null. Otherwise, I go this way. Okay, this is too short of a tree for me to simulate. Let's do this. Okay, so for 2, we are going to reach 9. So I'm in 2. I only go left when right is null. So right is not null, go right. Right is not null, go right. And here we reach this. So what if our 4 is null and our 9 is null? Well, now that our 8 should be null. Okay, I really can't read. Okay. So I only go left when right is null. I only get left when right is null. I only go left when right is null. Then we reach this. And then now we reach this. We point this to right. Right? And I don't even need to care about whether you have right or not. I just point you to null. Right? I think so. Because I need to increment to check 2. I need to then increment to check 3. Because I haven't flattened the left tree. All I did was just to point the last one to my right tree. So yeah, so I don't care whether your right tree is null or not. When I finish this, I reach to the end. So now let's do another step and point it to the right tree. Do I need to comment on this? I don't think so. So but it's easier to understand. And point the right to my right tree. Now I can cut off my left. After I cut off my left, I will increment to the next one, which is to the right, and then continue. So consider these are the same. I probably can just do everything inside a left is not null, but I don't want to modify it right now to confuse myself. Let's check the code first. Compile error. Why I always have compile error? Huh? 34. Oh, what am I doing? Why declare that again? 20. I have so many typo. What am I doing? Uh-oh, 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 27. 27. So what if the left is null? But the left should not be null. So I have exception in 27, which means my left last is null. But so weird. So if its left is null, then I change this to right. Then I make it right. Oh, okay. So if left is null, then we don't need to do anything in increment. But what if right is null? Do I need to care? No, right? So now I'm sure. Okay, but this one. So for the first entry of this loop, of course I know left last won't be null. But when I'm trying to find it, I need to make sure that so when right is not null, then I increment to right, to left. Okay, so when right child is not null, I increment, otherwise I increment to left. I make it the other way around. But what if left is null too? No way, because they could not be both null. Okay. Wow, that's pretty bad. So I have 1, I then null, and I have 5. How come? Why my 1 is still point to 5? Oh, I point my left, right to that, right? So I don't make it null yet. I will. Okay, I will have a temp. Okay, so do I need a temp? Tree node temp equals to root, right? And root equals to root dot left, and oh no 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 what I'm doing. So I point my last one to my right. Oh, I point my last one to my right. So now I have something to keep the right. Now I will point my right. Okay, I don't need the. Oh, I'm confused myself. You want to point the right to your left? Yes. I will point the right to the left. And then I will null out my left. And then my root will increment. Oh, that's so confusing. Let's check again. So I point my last one's right to my right. Now I have some. Now I can modify the right? So I modify the right to my left. Now I can modify my left, right? So now I null out my left, and then this current node is done. So I increment to my next node. Okay. Better. Do I need more example? Let's just use this. Okay, better. Okay, so I guess that's it. Let's try to submit it. I think there's no exception that we didn't deal with. Oh yeah. Okay, so now we already know the time complexity and space complexity. Let's directly look at the solution. See how they do it. So of course, first one is recursion, right? That's of course. But I think my recursion is not that good either. I mean, I confuse myself, so yeah. Why other people's recursion is always shorter than mine? I remember I did too many things that I don't know. Okay, yeah, but it's still similar. I think you return this, but what I did was that I want to make sure this is not null, because my recursive call, I don't want to deal with this. So yeah, so that's why our logic is a little bit different. Then you can change the recursion to an iterative solution using a stack, right? So we know this too. So it's a good practice probably to implement your own stack so that you have a control over how much space that you use, instead of that recursion decide what space that you are using. So this one, I think we are good. We don't need to look at it. And this one is our solution. Yeah, so you are pointing this. Yes, you are pointing your last one to your right. That's correct. Eh? What is this? Let's look at the idea of our current simple tree. So you point 6 to 1. Why? With the recursion, we don't get this connection until the left. For the current node, we will check if the left child or not. If it does, we will find the last node in the rightmost branch of the subtree rooted at the left as the. Once we find this rightmost node, we will hook it up with the right child. So I somehow think it's a little bit different with our solution, right? They are trying to find the rightmost, but rightmost is the last. What's the difference? So why are you pointing? Let's say our current node is root of the tree. The new does have a left child, so we will find the final node in the rightmost branch of the rooted. Another way to word that is we will keep on moving along the right branch starting at 2 until we find a node which doesn't have a right child. Once we do find this node, we will hook up its right node. Hey, so their solution is different than ours. The LeetCode teacher, I don't think I will ever get it. Well, people say that it's thin though, although it's 100% cotton, but they say that it's too thin. So I'm not going to get it anyway. I mean, I don't want to like walking on the street and have a mask on and let everybody know that I did LeetCode at home. It's weird. So yeah. Maybe a LeetCode mask. Okay, I totally don't understand this. I totally don't understand this. Already? Well, the coin I use, if you didn't notice, I used the coin to get my time travel ticket. And I already used 3 of them. So yeah, I am thinking that, really? I'm thinking that I'm going to save my coins to do this time travel ticket. Okay. I somehow don't understand this. Because my idea is to mimic whatever I did with the recursive call. And their idea didn't come directly through the recursive call. So Morris traversal. Is this something that we need to study? I guess Morris traversal is something that educate.io is something that to make sure that your traversal is only using constant space, right? I think. Yeah. Okay. Morris traversal. So we probably, there will be one day that we need to study this. So it could be a follow-up. Well, but it could be a follow-up in your interview, right? So you start by doing a really simple DFS practice, and then you think, oh, it's good, it's an easy question, and then suddenly the interviewer throw this to you like, yeah, because it's based on this, right? So you will start doing a recursion, and then the interviewer will probably ask you, can you not using a recursion? Then you do an iterative, and then if you do it too quickly, then you might get a you might get this last question. Hey, can you flatten a tree in O1 extra space? And the Morris traversal, I think it's hard because, I mean, you see, they said Morris in order traversal. So once you learn this, you probably need to also learn how to do a Morris pre-order traversal and then how to do a Morris post-order traversal. I believe that's different, right? That's similar, but that's different. It's not like recursion that when you are doing different traversal, you just move the three line in different position, right? And then that's a different traversal. But for Morris traversal, I think every time you change the order, it's a totally different thing. So I'm not going to do that until I was asked. Until somebody asked me in the interview, then I will try to show that I understand, but I probably won't be able to finish the code. I don't think so. Yeah, I don't think so. Well, I think for Morris traversal, it's probably okay for you to just give the interviewer your idea, right? You know that Morris traversal is that you point to the end of your previous traversal to potentially start of your next traversal, right? So once you link that, then you can forget about the current node because you are guaranteed that when you finish traversal of your left hand child, you are guaranteed that you will reach your next traversal, start of your next traversal. So I think as long as you can convey this idea to your interviewer, you don't need to worry about really implementing the Morris traversal. I don't know. Yeah. But I think this is something that we could learn, right? So what was a medium question could suddenly jump to a pretty hard, probably not hard, but it's a pretty hard, well, not, at least not too medium for me question. So yeah. Okay, so today we need to sleep early because tomorrow, like few hours later, we will have a first contest, and then 12 hours later we will have another contest. So good. That will be today's daily question. And I will not see you tomorrow in the contest, but I will see you tomorrow again for the daily. And then cry about the result of that contest together. Okay? Okay, that's the plan. Okay. Good night, everybody. Thank you for watching. Bye bye. See ya.